Greetings. In this video, I'll introduce you to molecular dynamics simulations. This type of simulation, for the most part, ignores all the complicated quantum mechanics and applies effective potentials that simulate particle-particle interactions. The topic is much larger and more complicated than I'm going to present in this video, and you should view this as a jumping-off point. I'll show you how to program a simple, inefficient molecular dynamics code, and I may or may not put a link to the code in the description. If I do, keep in mind that it's not guaranteed to be fast, efficient, good, or even bug-free. It's simply to illustrate how to think about these kind of problems. We'll start with Newton's equations. Each particle has a position r, which in general is a function of time. If the particles are moving, they also have a velocity, so their position changes like this. If the velocity is changing, they also have an acceleration, so the position and velocity evolve like this. I'll assume that you're already very familiar with these equations, but here's where we have to start. If we know the position and velocity of the particles at some time t, we can predict them at some future time t plus delta t, like so. Obviously, this is an approximation, and the smaller delta t is, the more accurate these updates will be. There are better update schemes, but I'll leave investigating numerical schemes as an exercise for the viewer. For now, we just want something that works. And now it's time to code this up. I'm using Python and Jupyter Notebook here because it's easy to see what's happening, and it's easy to screw around with things on the fly. I set it up with 5 particles, so n equals 5, and 3 dimensions, so d equals 3. You can obviously change these, it just seemed like nice system parameters. I set delta t equals 0.01. For a constant velocity, this doesn't really matter, since our update is actually exact. The positions and velocities are stored as arrays of positions and velocity vectors. I'll initialize the positions and velocities randomly, and they end up looking like this. Each time we update, the position changes by some amount v times delta t. Right now I just have it printing positions. So far this looks utterly unimpressive, but it's the core of our molecular dynamics simulation code. One of the fun things about molecular dynamics is watching the particles do things. I've modified the code to add a 3D plot of particle positions. This is a pretty bad way to visualize molecular dynamics simulations, but let's see how it goes. I just added some calls to matplotlib and set it up to update the plot with each iteration. You'll notice that I also defined a length of the system LL. While this is running, notice that the particles are just drifting off screen. There's nothing to stop them from doing that, and that's what we'll fix next. In order to keep the particles in our box, we need to decide what happens when they try to leave, i.e. the boundary conditions. There are a few directions we can go with this, but the simplest and most common are reflecting or periodic boundaries. Periodic boundaries are like living on a torus, or in a Pac-Man universe. When you go through a wall, you appear on the other side. Note that the actual positions of the walls is arbitrary. If you need to convince yourself of this, consider what happens when you shift the walls of the system over by some amount. The particle positions don't actually change, they just go through the wall as appropriate. Where you choose to put a spotlight on a periodic universe is irrelevant, as long as you light up a periodic unit. Anyway, periodic boundaries are useful when you're looking at crystals or other systems with periodic symmetry, but they're also useful when studying bulk systems that, on average, have translational symmetry, which is a special case of periodic symmetry. They can be implemented by a simple mod function, like I'm about to show you. Implementing periodic boundary conditions is as simple as adding this one line to the code. Note that I also added a flag BC so I can turn off the periodic boundaries if necessary. The particles no longer fly out of the box. Now when they encounter a wall, they just go right through to the other side. As I mentioned before, this isn't the only thing we can do. Reflecting boundaries are more like putting actual walls at the boundaries, and particles just bounce or reflect off the walls. Note that upon reflection, the velocity and the position both reflect about the plane. To implement the reflecting boundaries, we simply need to see when a particle hits the wall, and when it does, make the particle's position and velocity reflect about the wall. I've introduced a new subroutine that does just this. I first copy R and V, and then I go over every particle and every dimension to check if the particle has gone past a boundary in that dimension. If it's gone past the lower boundary, i.e. if the coordinate in the jth dimension is less than 0, I reflect the position about 0, and I set the velocity to point into the box, i.e. make its component in that dimension point in the positive direction. This reflects the position and the velocity. It's similar if the particle tries to leave through the upper boundary. If the jth coordinate goes past Lj, the new jth coordinate is set to 2Lj minus Rj. This is equivalent to the picture I showed previously. Once again, the velocity is set to point inwards. In both cases, I could have just flipped the sign of the velocity component as opposed to forcing them to point inwards, but I did it this way. Upon running the code, we see that rather than teleporting from one side of the box to the other, the particles bounce off the sides. So far, our visualization sucks. I could try to make a better Python visualization, but the point of this video is not to create a nice simulation program in Python. The point is to get you comfortable with MD itself. To that end, I'll show you a nice way of visualizing your results using a program called OVITO. We want to create an output file that looks like this. This is a standard format that you'll see from simulation software like LAMMPS. It holds the time step, the number of atoms, the box boundaries, and a list of atoms with their attributes. The box boundary types here are shown as PP, which means periodic, but other types are available. The atom attributes include position, but also the type of atom and the identifier for the molecule that it's attached to. I'll get back to these where relevant. The code to output such a file looks like this. You can run this subroutine whenever you want to see what your system looks like. Note that all the boundary condition stuff is now in the update routine. Once the files have been created, we can open them in OVITO. Just Google OVITO or check the description. It's free to download. You can open the file in the same way that you open any file in any program. You get 4 different visualizations to make it easier to keep track of the simulation, and you can change them if you want. You can open more files at once to make a video, and you can play around with the visualization stuff. You can do a lot more than I'm showing here. Just play around with it. You can also export images to a video or image file. I recommend playing around with OVITO a bit if you're interested. There are other visualization options. I just kind of like this program. So far, we've considered non-interacting particles, but that's all about to change. In order to model particle-particle interactions, we need to introduce some kind of two-particle interaction, Pij. A common and very useful choice is the Lennard-Jones potential, or 12-6 potential, as shown here. It has a short-range attraction, and then a very short-range repulsion, essentially a cutoff where the potential shoots up and it acts like a hardcore repulsion. A careful choice of epsilon and sigma proves surprisingly successful when modeling a variety of types of atoms. We'll get back to the specific values later, but for now the form of the potential is enough. There are lots of other two-particle interactions that are used in molecular dynamics, and one little video is not going to go into lots of detail, but it's easy to Google types of potentials used in molecular dynamics. The potential energy of a particle I at position r is given by the sum of the Lennard-Jones potentials between it and all the other particles. I've labeled this potential as ui. The force on the particle is then given by the negative gradient of ui. dp dx is given by the function shown here. The y and z derivatives are similar, just replace x by y or z. To put it another way, the gradient of Pij is given by this vector, where x hat, y hat, and z hat are the unit vectors in the x, y, and z directions. So in the simulation, for each I, we simply loop over all j, calculate a vector of distances, xij, yij, zij, calculate the stuff in the square brackets, and multiply them. The sum of the result is the force on the particle I. If you didn't follow all that, hopefully it'll be clear shortly when I show you the code. Since we're using Lennard-Jones potentials, we have the Lennard-Jones interaction parameters, epsilon and sigma. I've just set them to 1 for convenience. We also have particle masses, which I've also set to 1, also for convenience. Now I have 2 new subroutines, one calculating the Lennard-Jones potential and another calculating the gradient of the Lennard-Jones potential. Both are written such that they're passed the index of a particle, I, and they're asked for the potential or the gradient of the potential that it feels. For the potential, I first calculate an array of vectors connecting a particle I to each other particle. This is stored in drv, or dr the vector form. I don't want self-interactions, so I remove the ith element of drv. Next, I calculate the absolute distance between particle I and the other particles. This is stored in dr. Then it's just a matter of plugging this into the Lennard-Jones potential. R6 is the r to the 6th term, R12 is the r to the 12th term, and I just calculate them in sum. The gradient of the Lennard-Jones potential is similar, but a bit more complicated. The first 3 lines are the same, the next 2 lines are similar, but I need r to the 8 and r to the 14. The next line comes in because of the vector nature of the gradient. drv is the vector xij x hat, yij y hat, zij z hat, or rather, it's an array of such vectors for all j. The transpose stuff is because of how I formatted the vectors. NumPy will treat them as matrices, so this takes care of the matrix multiplication. From here, it's just a matter of summing over all j and returning basically the force, the negative force. Note that the negative sign in the equation is not present in the code. This is because I defined drv as rj minus ri, not ri minus rj. Now, since we have a force, we also have an acceleration, and we need to update the velocity. The force on each particle is stored in this array of force vectors, and it's given by the negative of the gradient of the potential. So I loop over all the particles I calculate the gradient of the Lennard-Jones potential, and return the negative of that. The acceleration is the force over mass, and the velocity is updated. I'll start with 2 particles pretty close to each other, just hanging out in the middle of the box. And the result looks like this. The potential starts out attractive because the particles aren't too close, and they're pulled towards each other. When they get a bit too close, the potential becomes repulsive and they bounce off each other. As they get further apart, they're attracted and they slow down, eventually stopping, turning around, and going towards each other again. This repeats indefinitely, just cycling between potential and kinetic energy. The finite size of our time step and the fact that our update routine is not perfect means that we don't perfectly conserve energy. Our update routine assumes that the potential varies slowly on the scale of our updates. You can think of it like this. When the particles get close, before the velocities reverse direction, each discrete update in time might overshoot a little bit. This puts the particle further into the high potential area than it would go if we solved the equations of motion exactly. This gives the particle a bit more potential energy than it should have. If this does occur, it'll be repelled with a bit more kinetic energy than it had before, slowly ramping up the kinetic energy and slowly ramping up the energy in the system. The smaller our time step, or the better our evolution scheme, the better the system will behave, but no numerical scheme will be perfect in general. We can also run the simulation with more particles initialized randomly like in the previous examples. This time, rather than passing through each other, they bounce off or deflect. If you look closely, you can also see some evidence of the attractive potential when they get kinda close. There's one important thing to note about interacting particles with periodic boundaries. To see what this is, consider the particle I've highlighted in green and its interaction with the other particles. There's a pairwise interaction between this green particle and this other particle, i.e. some potential that it feels by virtue of it being a distance r away. But with the periodic boundaries, it doesn't just see the particle there, it also sees it through the wall, so which distance do we use? It gets a bit worse than that. With periodic boundaries, we're essentially simulating an infinitely tiled system, so in order to get the true potential of the green particle, we would have to sum over all the infinite numbers of copies of every particle in the box, including itself. This, however, is not practical. Fortunately, the Lennard-Jones potentials that we've been using are pretty short-ranged. If the length of the system is much larger than the decay length of the interaction, it's sufficient to simply consider the closest image of a particle and interact with that. Most interactions, probably any you'll be interested in, can be treated this way. When we get to adding bonds, the potentials won't decay away like this, but if, say, particle I and particle J are bonded together, we only want particle I to be bonded to the closest copy of particle J, otherwise it doesn't really make any sense. I mentioned this now rather than leaving it for later because I'm not actually going to fix the code to deal with the periodic boundaries properly. I'll leave it as an exercise to the viewer, and I'll stick with reflecting boundaries for the rest of the video. You may have noticed that there's a growing list of things that I've left as an exercise for you. Having only one type of particle in the system gets pretty boring. We can set up a simulation with particle types, say 0 and 1, and I've set the mass of particles with type 0 to be 1, and type 1 to be 10. If we set up a mass lookup table like this, we don't need to change the velocity update routine, we can just use this array. Our output subroutine now has a type output. Typically in simulations, you'll want to keep certain things fixed. This defines the ensemble. Basically, the ensemble is the set of all configurations that obey a certain description. You may want to keep the number of particles, volume, and amount of energy fixed. This is called the Microcanonical or NVE ensemble. This is basically what I've been doing so far. The way we set up our simulations, however, there may be a small drift in energy due to inaccuracies in our time step. We used a pretty bad numerical scheme, but even if we used a great one, none are perfect, and there would be some drift. This is bad, and in order to keep our energy constant, we need to correct for it. We want the total energy E0 to be constant. The potential energy is just a function of the positions of the particles, so we can't change that without moving them, but we can readjust the kinetic energy. For some E0, which we set at the beginning of the simulation, or change throughout, or whatever, every now and then we calculate the total energy in the system and thus the difference in kinetic energy between what we want and what we have. Then we readjust the kinetic energy like so. Unless our integration scheme is particularly terrible, or we choose a really large delta T, this adjustment should be very small. The forces themselves are conservative. I'm not actually going to implement this, but I'll do something related using a different ensemble. And there are other ensembles. For example, imagine your system is held next to a heat bath at constant temperature. Energy flows into or out of the system in order to keep the temperature of the system constant. But how do we keep the temperature constant in our simulations? It's the same kind of thing as before, but instead we want to keep the average kinetic energy a constant. As we know from the equipartition theorem, energy spreads out so that each degree of freedom gets, on average, a half kT of energy. We have a bunch of translational degrees of freedom, here one per dimension per particle. The total kinetic energy should therefore be 3n over 2 times kT. But this is equal to the sum of half mv squared, or the other way of finding our kinetic energy. Setting these equal, we can relate the average square velocity to the temperature. So the system is at some temperature T, but we want it at some other temperature T0. Changing the temperature is as easy as scaling the velocities. If we divide these two equations and simplify, we can arrive at some scaling factor lambda. So now we just multiply our velocities by lambda, and the system is now at temperature T0. So far we haven't cared about units at all, so our actual masses, interaction parameters, and times have been meaningless. Now that we want to stick in some real constants, like masses and Boltzmann constants and temperatures, we need to start thinking about units. I'll set the unit length in the simulation to angstroms, the time to picoseconds, and the masses to daltons. Now we need to convert the Boltzmann constant kb to those units. I laid out the steps here just to make it clear. I also plugged in some epsilon and sigma values for the Lennard-Jones interactions, as if the particles are hydrogen. I just googled the Lennard-Jones interactions for hydrogen and used the first result. I'll leave the link in the description to the source. The actual subroutine to correct the temperature looks like this. I find the total kinetic energy, half mv squared, and use that to find the average kinetic energy, and thus the current temperature, T now. This then gives me lambda, so I can rescale the velocities with that. The line I've commented out is for if I want to update the temperature more slowly. Rather than setting the temperature to exactly T0 every step, I can make it a little bit closer to T0 every step. Anyway, let's run this at a few temperatures and see how it goes. This is what a system of 20 particles looks like at different temperatures. I've colored them differently just to make the visualization nicer. At higher temperatures, they bounce around a lot more, as you would expect. At lower temperatures, they're a bit more subdued. At even lower temperatures, the random motion's not sufficient to overcome the Lennard-Jones interactions, or the attractive part of it at least, and the particles condense together into little jiggling globs. If you want to simulate molecules, not just atoms, we need to add some bonds. Bonded atoms tend to be a certain distance apart, set by the molecular orbitals that form the bonds. I've labeled this distance as Lb. The bond length is not some fixed amount that can't ever change. Rather, there's some energy penalty to deviating from the distance, also set by the molecular orbitals. I've approximated it as a simple spring potential. This is a simplification, and you can consider it a quadratic expansion around the true bond potential. which is a lot more complicated. This, however, turns out to work well for many purposes, so that's what we'll use, but you can swap it out for other better bond potentials if you want. The strength of the bond potential between atoms I and J is given by gamma ij. Gamma ij is obviously 0 if the atoms are not bonded, and some positive finite value if they are bonded. As before, we can differentiate this to get the force and add it to our equation of motion. Calculating the bond potentials requires a list of bonds. I've stored them in this array. A bond is described by each element in the array BND. Each bond description is a list where the first element is an atom ID, the second element is the atom that it's bonded to, the third is the length of the bond, LB, and the final element is the bond strength, gamma. Calculating the bond energy is done like this. I loop over all particles, I, and for each particle loop over all bonds, labeled J, and see if the particle I is in any of these bonds. The bond parameters are assigned to variables, just to make it nice to look at. Next, I find the distance between particle I and the particle it's bonded to. Then just plug this into the bond energy equation. Note the half here due to double counting the bonds. I could have done this more efficiently. Calculating the force from the bond potential is similar. I first initialize an array of gradients of the bond potential, and then it's pretty similar to the bond potential. I loop over every particle and see if it's in a bond, calculate the distances, etc. The difference is in the last line here, where I multiply by a vector. Now let's do something almost realistic. We can set the bonds and the Lennard-Jones potentials to those relevant to water and let it run. The source for the parameters is in the description. I initialize the positions randomly and just let the atoms find the ones they're bonded to. This is easier than thinking about where the atoms should actually be placed, and I'll keep doing this throughout the rest of the video. This simulation does not look remotely realistic. The hydrogen atoms are just flopping around all over the place, and there are no hydrogen bonds. This is because a fair amount is missing from this simulation. For one thing, the bonds shouldn't just point in any direction. To see why, let's go back to what a bond is. The bonds are formed by molecular orbitals. Oxygen, when bonding to hydrogen, forms sp3 hybrid orbitals that look like this. There are a total of 4 orbitals that can each hold 2 electrons, and there are 6 electrons. The half-fill orbitals overlap with the 1s orbitals in the hydrogen atoms, forming molecular orbitals that connect the oxygen and hydrogen atoms, i.e. they form covalent bonds. The hydrogen atoms therefore attach here to these orbitals. This is what sets the bond angles. Don't worry, this is the last quantum mechanics you'll hear about in this video. You end up with an atom that looks like this. Once again, I don't want to include quantum mechanics in the simulation, so I just set a preferred angle, 109.5 degrees, which is set by the orbitals, and I set an energy penalty associated with deviating from this angle. This is essentially the same as what we did for the bond lengths. The magnitude of the energy penalty is controlled by kappa, and theta 0 in this case is 109.5 degrees, as I mentioned. I've labeled it as IJK because this is a 3-body interaction between 3 atoms that form the angle. The value for kappa is in the link in the description. So now we have the positions of 3 atoms with some quadratic potential for the angle, and we want to derive an equation of motion for the atoms. I'll show it for the end atom, which I've labeled 1, and the middle one, which I've labeled 2. The vectors defined here are R1 and R2, giving the positions of the atoms 1 and 2, and delta R1 and delta R2 giving the relative positions of the end atoms and the middle atom. I've labeled the components with a similar scheme. The code contains the positions of the atoms, but it's easy to find the angle theta from the dot product of the bond vectors, delta R1 and R2. Consider the fact that changing the position of atom 1 in general changes the bond angle, which then changes the bending energy, so we need to relate the change in the position of the atom to change in the energy. I don't want to go through the whole derivation, but essentially you start with the chain rule, and after a bunch of algebra you end up with this expression. There are similar expressions for the y and z coordinates, just swap out the x's for y's and z's, and this gives you the gradient of u. And it's similar for the particle at the center of the bond. Again, note that moving the particle in general changes the bond angle, and this allows us to relate the gradient of the potential to the derivative of the potential with respect to the bond angle. Once again, I won't go through all the algebra, but here's the result. Also, once again, I've only shown the result for the x-coordinate. but you basically just substitute y's and z's in place of the x's to get their derivatives. Much of how we treat bond angles is similar to how we treat bond lengths. First, we need an array of angles that we care about, giving the 3 atoms that are bonded together, the preferred angle, th0, and the penalty for deviating, kth. As you can imagine, the subroutine for calculating the force is a little more involved, so I'll break it into parts. Overall, we do much like we did for the bond potential. We create an array to store the gradients for each atom, I, loop over all angles and see if atom I is either of the end atoms, A1 or A3, or the middle atom, A2, and we treat the ends differently from the middles. Before we split into end versus middle calculations, there are a few things we want regardless. We want the equilibrium angle, Th00, the bending modulus, E0, or kappa in the discussion. We also want the bond vectors, R1 and R2, which are equivalent to delta R1 and delta R2 in the analytical expression. And I've set it so R1 points to atom I, if I is an end atom. We also want the absolute length of the bond vectors, AR1 and AR2, their dot product, N dot, and the angle between them, theta. We could also calculate the negative of du d theta now. I've rewritten the previous equations in a way that makes it clear how I combine them in the code. Numerator is just the numerator in this big fraction, and denominator is the denominator, i.e. it's just sine theta, but written in terms of what's easily accessible, i.e. cos theta. And recall that the minus sign is already in the variable du d theta. So far we have 2 particle bonded interactions, which are just bond potentials, 3 particle bonded interactions, i.e. bond angles, but there's yet another bond potential that's often included, dihedral angles, which are a 4-body interaction. So now imagine that you have 4 atoms bonded together like this, and I'll label them 1, 2, 3, and 4. You can define a plane that intersects atoms 1, 2, and 3, and another plane that intersects atoms 2, 3, and 4. The angle between these planes is the dihedral angle. This time I'm not even going to try to include it, but you should know that when you're dealing with molecules with more than 3 atoms, dihedral angles will come into play. Many atoms also have charges. I've framed this in terms of water, but charge is obviously a lot more general, and if you want to do molecular simulations, including ions and things like that, becomes relevant. In the case of water, the oxygen atoms are a bit more electrophilic than the hydrogen atoms, so more of the electron wave function is around the oxygens than the hydrogens, making it slightly negatively charged, while the hydrogens get a slight positive charge. If we want to simulate interesting molecules, we need to include charges. The Coulomb potential between 2 charges looks like this, proportional to the product of 2 charges and inversely proportional to the distance between them. We can derive the force, or just look up the Coulomb force, and we get an expression like this. Note that this fraction is basically just a unit vector, but it's convenient to use it in this form in the code. For the Coulomb interactions, we need a list of charges, i.e. a list of which atoms have what charge. I also set it so the atoms in the same molecule don't feel the Coulomb force from each other. For that, you'll need to assign atoms to molecules. Once that's all set up, it's quite simple. The Coulomb force on an atom is given by the sum of the pairwise forces. If you can follow the Lennard-Jones subroutine, this should be simple. So pause and have a closer look if you want. Finally, we can stick all this together. We have Lennard-Jones interactions, bond lengths, bond angles, and Coulomb forces. The intramolecular interactions are all defined by the bond potentials, so I've turned off the Lennard-Jones and Coulomb forces between atoms in the same molecule. Now, let's see if our water looks any better. Here are some water simulations done at different temperatures. At high temperature, it looks gaseous, and at low temperature, the molecules begin to aggregate together. We're not going to get any real phase transitions here. There are too few molecules, and it would be better to conduct the simulations at fixed pressure, not fixed volume. But you can just add that to the long list of things left as exercises for the viewer. If you do want to fix the pressure rather than the volume, you have to change the size of the simulation box. When the particles hit the side, they transfer momentum, i.e. apply a force to the wall. Pressure is the force per unit area, so you need to adjust the walls so the force, given by the momentum change of the particles hitting it per unit area, is constant, and equate that to whatever pressure you want the system to be at. Linking more atoms together allows us to simulate polymers. I've included a simulation of 4 decane molecules and another of a 40-carbon polyethylene molecule. Note that I've ignored the dihedral angles, so this isn't totally realistic. The third simulation is simply a set of particles strung along. When simulating polymers, it's often actually advantageous to think of them like this and ignore the atomic degrees of freedom. Or you can just think of them as strings through space. Each bead here represents a set of atoms, maybe a monomer or a set of monomers. One thing that I've left off of the simulation that's crucial if you want to have any chance of simulating systems that are not trivially small is a cutoff for the potentials. Lennard-Jones potentials, for example, become irrelevant if particles are more than a little ways apart. So why are we calculating forces between pairs of particles that are much further than this? Coulomb forces decay slower, but still pretty quickly. Most of the forces that we're calculating are orders of magnitude smaller than we would actually care about. In most simulations, you therefore define some cutoff distance and don't bother calculating the interactions with particles further than that. Once again, I won't bother to actually do that, but it's simply a change to the loops over which the potential calculations are conducted. There is one other thing that I want to mention. I've framed this simulation tool as a molecular dynamics simulator, but it's a bit more general purpose than that. You can, for example, plug in gravitational interactions. For this example, I made particles interact gravitationally, plugged in objects with masses of the planets and initial velocities that they would have in their orbits, and just let it run. There are many things that you can do with this kind of simulation. Just set the interactions you want and let it run. In this video, I've shown you how to program a simple molecular dynamics simulation. I may or may not have included the code. If I did, then it's in the description. If not, then it's not. The point of this video was not to produce a production quality simulation. The code is not meant to be fast or efficient or well written or even necessarily bug-free, just kind of easy to understand. The point is to give you the understanding that you need to know what you're doing when using real production quality code. If you want to keep playing around, you can try improving the code in the ways that I mentioned throughout the video. Use a better numerical scheme, fix the interaction through the periodic boundaries, implement other ensembles like the Microcanonical, or fix the pressure rather than the volume, add dihedral angles, and add in a range cutoff for the interactions. These videos are pretty to look at, but if you want a simulation to be useful, you have to extract useful information from it. You'll want to get thermodynamic variables, things like pressure or heat capacity. You may want to characterize the organization of particles, maybe study phase segregation in different types of molecules, like water and mixed with alkanes. If you want to study phase transitions, you'll need order parameters. Further, with molecular dynamics, you can study transitions between phases, so you'll need ways to characterize the transition rates and mechanisms. These are just a few examples of quantities you can study, and what you'll need depends on the problem you're interested in. If you decide to do molecular dynamics simulations, please don't do what I did here. Don't write a poorly cobbled together, barely tested, inefficient simulation code in Python. For the purposes of learning how MD works and for the fun of playing around, it's great. But these simulations are nowhere near production quality, and there are fast, efficient, well-written, well-tested programs ready to go. Assuming I get around to it, in the next video I'll try to bridge the gap and introduce you to a few options that are commonly used in research.